Okay, let's look at another example. Hourly pay, comparing a population distribution to a sampling distribution. The mean hourly pay rate for financial managers in the East North Central region is $32.62, and the standard deviation is $2.32. Assume that these pay rates are normally distributed. Part A says, what is the probability that a financial manager earns between $30 and $35 per hour? It says, what is the probability that a financial manager, X be the random variable that represents a manager's pay rate. So this is an individual pay rate. Now, we notice that in this problem, we're given that the distribution of this random variable is normal. We're given the mean at $32.62, and we're given the standard deviation as $2.32. Now, this is actually a problem that we did in the last chapter. The average is in the center, it's normally distributed, the standard deviation is $2.32. Okay, and they want the probability that a manager's pay rate is somewhere between $30 and $35. So $30 is roughly one standard deviation to the left, roughly, and $35 is, well, roughly one standard deviation to the right. Not quite, we'll have to see how many by calculating their z-scores. So the z-score for 30 is 30 minus 3262 divided by $2.32, and that gives me a negative 1.129, which I'm going to round to a negative 1.13, and then the z-score for the 35, and I get 1.025, which I'm going to round to 1.03. So the 30 is a negative 1.13 to the left, or 1.13 standard deviations to the left, and 35 is 1.03 standard deviations to the right. To find the probability of being in that interval, I need the area under the density function above the interval. Of course, my table works out of the center and only to the right, but we do have, actually we don't quite have symmetry here. 30 is at a different distance from the center than the 35, so I'm going to have to look up both of these. First thing I'm going to do is look up the 1.03, and I'll be able to get the area of this side. 1.03. Okay, 1.03, so I'm down here in row 1 and the column 0.03, 0.3485. So this side right here is 0.3485. Now to get this side, I'm going to have to look up again, there's only positive z values in the table, but I'm going to need to look up a positive 1.13. So a positive 1.13 would be down here in row 1.1, and again over to the 0.03 column, and I would have 0.3708. So 0.3708. Now to get the total probability, or the probability that z is between a negative 1.13 and 1.03 would just be 0.3708 added to 0.3485, and that would be 0.7193, or 71.9% approximately. Part B. What is the probability that a sample average taken from a sample of size 30 financial managers is within 75 cents of the $32.62 population average, or population mean? So in this case, we're talking about the random variable x bar, which are sample means taken from samples of size 30. And we have the sampling distribution, which we know is normal because the sample size is at least 30. And the center of that distribution is the population average. But the standard deviation is called standard error. And that is the population standard deviation, which we have as a 232, but divided by the square root of the sample size. And we have 0.4236 as our standard error. Now, the question is, what is the probability that if we take that sample of size 30 managers and we average their pay rates together, that average will be within 75 cents of the $32.62. So I'm going to add and subtract 75 cents. So that's at least 1.5 standard deviations. So I'm going to put the marker out maybe about right there. 75 cents and then 75 cents to the right. I can see that I'm going to be the same distance from the center, so I will have symmetry. So I'm talking about the probability that X bar is between $31.87 and $33.37. And to find that probability, I'm going to find the area under the density function above the curve. But I can use the standard normal table because, one, I know the sampling distribution is normal because I'm using a sample size of at least 30. I know the mean, which is 3262, and I know the standard deviation, which is the standard error when you're sampling, 4236. So to find the probability, I'm going to go to the standard normal table, and I'm going to, in this case, because of symmetry, I'm just going to look up the 3337 and then know that the area to the left of the center is going to be the same, going down to the 3187. So let's find the z-score of 3337. Of course, the difference there is just 75 cents. And then divided by the 0.4236 equals 1.77. So the z-score for the 3187 is a negative 1.77, and the 3337 is a positive 1.77. But I just need to look up the 1.77. So 1.77, I would go down to row 1.7, and then over to column 0.07, and I would get 0.4616. So I know that both of these sides is 0.4616. And the probability that X bar is within 75 cents of the 3262 is the probability that Z is somewhere between a negative 1.77 and a 1.77. And that would be 2 times 0.4616, which equals 0.9232. So we're going to look at both of these, part A and part B. The first part was talking about the probability of an individual manager's pay rate. So I was talking about the population distribution, and the standard deviation is 2.32. But in part B, I was taking a random sample of 30 managers at a time and calculating the average pay rate for the 30 in each case. So the distribution of those sample averages although it's normal, has a different standard deviation. It's called the sampling distribution. The standard deviation is 0.4236. So working that, I'm really answering two questions here, two different questions. There is some similarities, but there's some distinct differences. One case, I'm talking about the probability of an individual being in an interval, and then in the other case, I'm talking about the average from a sample being in a certain interval.